On BBC Learning. And now another adult educational programme in studies on BBC Learning.
To be or not to be? That is the question. Or is it?
Hamlet was supposed to have pondered life and death here at Elsinore Castle, but Shakespeare's Prince of Denmark wasn't the only one to find inspiration on the nature of existence here.
Another Great Dane really did walk these grounds as he struggled to understand the world, and he reached some extraordinary conclusions.
There's to be, and there's not to be. But there's also something in between. Maybe to be. An odd, mysterious uncertainty at the heart of nature. Something that Albert Einstein fought for years to disprove. This is the story of the most spooky, strange, and profound theory in physics. Quantum mechanics.
Without quantum mechanics and without a knowledge of how to use quantum mechanics, there will be no mobile phones, no CD players, no computers. All of these rely on the properties of quantum mechanics.
Quantum mechanics as a mathematical description of the world is the most successful scientific theory we've ever had. There are no experiments that I know of that contradict the theory. It forces us to confront those deep issues of existence, and it's not just a matter of a mathematical recipe for describing the world.
It is the greatest revolution in science, greater in some sense than relativity theory. You see, relativity theory was in the crown of the 19th century. Quantum mechanics is the crown of the 20th century.
Countless things we take for granted in our everyday lives wouldn't be here if it wasn't for quantum mechanics. It's the theory that predicts how the world behaves at an atomic level. And it gave birth to a second industrial revolution with the invention of modern electronic devices. But quantum theory caused another revolution. Now, we're all used to nature being certain, dependable, predictable, but the tiny quantum world just isn't like that. What happens inside an atom is just plain weird. It puzzles everyone. The journey to understand quantum theory is the story of a battle between two of the greatest physicists in the 20th century. In the 1920s and 30s, Einstein fought a battle of ideas with someone you may not have heard of, who was born in this street in Copenhagen, Niels Bohr. He's so famous, they even put him on the money.
Niels Bohr was one of the giants of 20th century physics, and so we have these two hugely influential figures, Bohr and Einstein, at loggerheads, friendly loggerheads, but fundamentally disagreeing about quantum mechanics.
They were very fond of each other. They respected each other highly. But, you know, as soon as it came on quantum, the sparks would fly.
Einstein felt that certain aspects of quantum mechanics, the world as presented by quantum mechanics, didn't really make philosophical sense. The world being presented by quantum mechanics was too ugly to be true.
For centuries, scientists believed that nature was predictable. If only we knew enough about the way the world worked, we'd be able to say exactly what would happen in the future. It seemed obvious that nature was deterministic. One thing determined another. But quantum mechanics shattered that certainty. It upset people then, and it still does now.
It was a complete shock to hear quantum mechanics had this weirdness beyond the straightforward weirdness that we've been told about in the course. And I can quite understand why Einstein spent most of his life doubting it.
Albert Einstein was an early pioneer of quantum theory. He showed that light exists as tiny quantum particles called photons. Einstein went on to be famous for relativity theory, E equals mc squared and all that. But who was Niels Bohr?
Niels Bohr was born in Copenhagen in 1885. He was the son of a prominent professor at the university. Bohr's contribution to quantum mechanics from the outset was his formulation of a model of the atom, and particularly the hydrogen atom. And that was essentially the work that he received the Nobel Prize for almost 10 years later in 1922. Although his ideas tend to be misunderstood at times, he's an icon, I think, of this century in Denmark, perhaps the most well-known Dane within Denmark.
Bohr was not just a father figure to me personally, which he was, but he was a father figure to a generation of physicists. His institute was the Mecca, the most important center of physics in the 1920s and 1930s. Practically everybody of my generation, the younger generation, two younger generations, they all came to Copenhagen. And they worked together.
It must have been truly wonderful that so many new areas of investigation were opening up, that you could pick almost any topic and apply the new sciences of quantum mechanics and relativity to them and get almost instant results.
It was as if you had hit on a field of gold. You just grabbed something up and there were nuggets of gold in your hands. There were problems that could be solved that never could be solved before with a new theory, and people went one after the other. In other words, it was a time in which you could make a great name much more easily than in later years.
But there was a high price to pay for the success of quantum theory. Trouble was on the horizon, not least for Einstein and Bohr. They were founding fathers of the quantum physics, and in the early 1920s both got Nobel Prizes for their work. On the way to Sweden to pick up his prize, Einstein stopped in Copenhagen to visit Niels Bohr.
And that's the first time Bohr and Einstein met personally. Would you like me to tell a story about that? Bohr went to the railway station to pick up Einstein, and they took the streetcar, Bohr's home. So they were so busy talking that they went many stops too far. And Bohr said, we have to go back. They took the other tram car and went back, went again too far, and back and forth till they finally stopped at the right place. They were so involved in their discussions.
An argument was brewing that would divide them for the rest of their lives. Although both leaders in their field, their ideas were leading them in opposite directions.
As Niels Bohr became the most prominent champion of quantum theory, Einstein became its most famous doubter. Einstein didn't so much disagree with the theory, he thought it was incomplete. It was saying the wrong things about the true nature of reality. So what was quantum theory saying? The theory states that there is an absolute limit to what we can know about what goes on in nature at the atomic level. It says the universe is run on chance, that nothing is certain. Which means what exactly? To give you an idea of the difference between the ordinary world and the quantum world, imagine that inside this tin is an ordinary glove. Now, it's either left-handed or right-handed. The obvious way to find out is to have a look. All we've done is reveal what nature already knew. That was the nature that scientists and the rest of us were used to. But in the quantum world, it ain't that easy. Now imagine that inside our tin is a quantum glove which behaves in the same way as a subatomic quantum particle does. Before we open the tin, there's an equal chance that the glove could be left or right-handed. Quantum theory says not only don't we know which hand it is, but nature itself doesn't know. In fact, in a way, the glove doesn't even really exist when the tin is closed. It's in some sort of ghostly state, in between being left and right-handed. It's only when we open the tin and make a measurement that a choice is made and it becomes one or the other. In the quantum world, it's not as simple as to be or not to be. Until it's observed, nature hasn't made up its mind. You think this sounds odd? Can't be true? Well, you'd be in good company because Albert Einstein would have agreed with you. He couldn't accept that nature was uncertain. That's what he was getting at when he said, God does not play dice.
I said, Professor Einstein, why can't you accept all this? He said, well, I know it is very successful, but I don't believe it is the last word. There's a deeper theory under all this. That was his opinion.
Einstein fought against the idea that nature was uncertain. Does that mean the moon isn't there if I'm not looking at it? Einstein would say. Bohr's position was, to paraphrase Hamlet, there are more things in heaven and earth than are dreamt of in your philosophy, Einstein.
I think the thing that Einstein fundamentally hated about quantum mechanics was the element of uncertainty or indeterminism. And I think that deeply offended Einstein, who felt that we live in an orderly universe which is fundamentally rational and that there should always be a reason for why things occur.
For hundreds of years, scientists had believed in a deterministic universe, that things happened for a reason and that the secrets of the universe were just waiting to be unlocked. But quantum mechanics said something else.
What quantum mechanics came to show physicists through the 1920s was that nature wasn't deterministic after all, that nature was genuinely chancy, that you couldn't predict, even if you were God and knew everything, what was going to happen next, that sometimes things went one way or the other completely on a random basis, and that was quite different from anything that had come before in physics. Some people just didn't believe it. Some people still just don't believe it. It scarcely makes sense.
In daily life, we're used to the fact that events occur always with well-defined causes. We may not know what the causes are, but if we investigated, if we had complete information about the system, we could say why something happened. Things don't occur spontaneously or arbitrarily. They don't occur for no reason. But in the quantum realm, they do occur for no reason. Generally speaking, from one moment to the next, you don't know what an atom or an electron is going to do. So indeterminism or uncertainty is the central feature of quantum mechanics.
Einstein didn't like that. He wanted what he called objective reality, that you could make a statement about physical world independent of the way in which you observe. And that was the crucial, fundamental argument between the two of them.
Despite Einstein's objections, the quantum theory was a huge success. Mysterious effects like radioactivity could be understood, and new technologies like microelectronics were being born. But what it said about the uncertainty of nature, nobody really liked. Everybody worried. What did it all mean? Niels Bohr would go on long, rambling walks, pulling together the ideas, trying to make sense of the theory that said, to be, not to be, or maybe to be.
It's not difficult to do the mathematics of quantum mechanics. It's incredibly difficult to try and understand the consequences of the quantum theory.
You have one attitude when you're working in the small, another attitude towards large-scale objects. And that works well enough. I mean, that's good enough for working physicists. But it doesn't really make philosophical sense because there's this question about what counts as small, what counts as big, and why do they work differently if the big things are just made of lots of small things.
Eventually, Bohr came to the conclusion that you've just got to accept that nature's odd. The theory might not make common sense, but you can't argue with its success. Stop the navel-gazing and get on with the job. His so-called Copenhagen interpretation of quantum mechanics became the new orthodoxy on the nature of reality.
Bohr's idea was that we could think of reality from two perspectives, or that reality kind of contained two alternative dimensions. So there was reality as it was at the microscopic level, and then everything behaved as quantum mechanics said, and things were wavy and didn't have definite positions or definite speeds. And then there was reality at the macroscopic level, and that was as we'd always assumed it. It obeyed classical physics. Everything was definite and unpuzzling. But somebody who's worrying about what is really going on won't be happy about that.
They were determined to solve this, but it was really hard to test the quantum ideas. 1930s technology wasn't up to the job. So instead, Einstein and his colleagues would test nature in their heads. To expose the flaws in Niels Bohr's philosophy, Einstein dreamt up elaborate thought experiments.
Einstein had a number of experiments, thought experiments, ideas, which were trying to bring out how weird, how odd, and indeed, from Einstein's view, how unbelievable was the picture being presented to us by the new quantum mechanics. The most famous is the EPR thought experiment, the Einstein-Podolsky-Rosen thought experiment.
The EPR experiment is a bit tricky to get your head around. Imagine the glove in this box is a tiny quantum particle. Only this time, we've got a pair of particles, well, gloves. Now, we haven't opened the box or made any measurements of the gloves. So according to Niels Bohr, neither of these gloves knows whether it's left or right-handed. They're in some strange state, a kind of mixture of left and right. We can't know anything about these quantum particles, except that, like gloves, they have to come in pairs. But before they're observed, the particles remain in a strange, unknown state. Okay, says Einstein, I don't believe it, but just suppose it were true. If I open one of these tins, we force nature to make a decision. Now, because the gloves must be a pair, the other glove must instantly become the opposite to this one. Its state is no longer uncertain. But how does this glove know when we open this tin? Can the gloves communicate? Maybe there's some special way we don't understand where they can send a message to each other. But even if that was true, the message can't travel faster than the speed of light due to Einstein's theory of relativity. But if we could open the tins at exactly the same moment, well, there'd be no time for the message to travel.
Now, that's instantaneous action at a distance, and modern physics, because of Einstein's own theory of special relativity, doesn't allow that. So Einstein was pointing out that if you believe quantum mechanics as normally understood, you're believing something that's inconsistent with special relativity, and that just looks wrong.
I said, Professor Einstein, why don't you accept this? It works. It works so well. He said, yes, I know it works so well. But he said, Newton had a wonderful theory which worked for 2 centuries, perfect, until I came along and I saw there were little things where it did not work so well. Well, so the fact that it works so well is not a guarantee that it is the truth.
The EPR thought experiment was Einstein's last and best challenge to the quantum theory. After 1935, he moved on to other things, but he remained unconvinced about the theory for the rest of his life, despite the efforts of Niels Bohr.
It bothered him tremendously that he could never convince Einstein. It was a real aggravation to him. He felt that he had failed because he couldn't convince Einstein. Now, it was in some ways Bohr's great fortune to have such a formidable opponent, because it forced him to make his language ever more precise.
As the theory was refined, it became more and more successful. Despite the philosophical difficulties, most scientists just got on and used it. But the EPR thought experiment remained. Einstein's challenge was untested for nearly 50 years, but it was not forgotten. In the 1960s, John Bell, a physicist from Northern Ireland, moved things on by turning the EPR experiment into something that could be practically tested. This was finally done over a tiny distance by a French team led by Alain Aspect in the early 1980s. In 1997, a team in Geneva attempted the experiment on a much larger scale. They tried to demonstrate that a pair of quantum particles actually do have a strange, spooky connection, this time across a whole city. If Nicolas Guizin and his team were right, then they would have proved one of the greatest scientists of all time was wrong.
Well, it's a long, long journey, of course, and it goes back to Einstein and even before. I mean, Newton, you can go back. And it's also certainly not the end of the journey. So if we go back to, let's say, Einstein at this time and Einstein-Bohr debate, at that time they had to swallow the revolution of quantum mechanics and to accept the new physics and the new views. And indeed, the paradoxes, like the EPR paradoxes. And well, my part of the journey probably was to test that, to understand it, to test it, and to participate to this new way of looking at quantum mechanics as a resource to produce new things, cryptography, computing, and so on. And with my team at Geneva University, we had a chance to test experimentally the issue. And I hope I will continue that journey.
For this experiment, they had to create a pair of quantum particles. They used photons, which are particles of light. Like gloves, one photon must be opposite to the other. The key was to separate them by 10 kilometers and then measure them at exactly the same moment. There would be no time for a message to pass between the photons.
So this is where the experiment started. We created our photon pairs and then sent them to the other stations where they are measured. It starts at a red laser, which you see here. Just see the reflex on my finger. And this laser light is then focused into a nonlinear crystal, which you find here. And this is actually the heart of our experiment.
The idea is to have 2 photons which are produced at the same time. In principle, you take 1 photon, and in a nonlinear crystal, you let it divide into 2 twin photons. There are 2 photons, but they together form one system, one quantum system.
One of the photons is then coming out by this fiber, going through the fiber network, which you usually use for phone calls, going all the way down to Bernay in this direction. The other photon is coming out here, again in the fiber network, going all the way to the other side to Bellevue, where we make the other measurement.
Going to telecom fibers gives us a possibility to go over long distances because these fibers are very well tuned for that. One village is near the Lake of Geneva and is about 5 kilometers north, and the other one is about 5 kilometers south. And so we have this 10-kilometer direct spatial separation. So if then on the north of Geneva, let's say on one side, we do a measurement, when the photon on that side acquires a property, and instantaneously in theory, and certainly faster than light in practice, the other one there also gets the opposite property. The output on one side is random, completely random. The outcome on the other side is also completely random. However, the two outcomes are always opposite. Not only do we not know which photon has which property, but according to the theory, well confirmed by the experiment, the photons themselves don't know. So in some sense, nature itself doesn't know. And we find that on this very rare occasion, Einstein was wrong.
So nature really is weird. Until someone makes a measurement, two photons can exist in a tangled up state, both being and not being at the same time. This entangled pair of photons are somehow connected across vast distances.
And the property still holds. Probably, according to quantum mechanics, if you go to the moon, it's still there. It's more difficult to test, but it's quite a fascinating prediction.
Einstein-nil, 4-1.
Poor Einstein, I'm sure he'd be very upset if he saw the results of the aspect experiment and these others that have been done, because it would force him to make a choice between his beloved theory of relativity that forbids faster-than-light signaling or his implacable opposition to the idea that nature is fundamentally indeterministic. It's fascinating to wonder which side he would come down on.
Bohr, one could say, was correct, but if you read his answer to the EPR argument, his answer was not very helpful. So he was correct, but maybe not very productive. Einstein, on the other hand, was wrong in some sense, but was productive. And sometimes it's better to be wrong and productive.
But there's more to all of this than settling an argument between two dead physicists. The weirdness of entangled nature may yet prove strangely useful.
I think the 21st century will be the century of quantum technology. We've seen the first of the quantum gadgets in our century, but many of them are like toys. You know, when the laser was invented in the 1960s, it was often called an invention looking for an application. And now, of course, we see lasers used all over the place. But it's still a novelty. I think in another 100 years, we're going to find quantum devices in almost every aspect of technology. And the weirdness of quantum mechanics, which we find so hard to get to grips with, is going to become manifest in everyday life, and we're going to have to somehow come to terms with it.
Quantum weirdness may become commonplace, but that doesn't mean we'll be able to understand it.
What else we're supposed to think? Nobody has any good ideas. I mean, that's the holy grail in this area, an interpretation of quantum mechanics that will make sense of what's going on and not be inconsistent with special relativity. The philosophers haven't come up with anything, nor the physicists. We're all stuck. Only some of us worry.
Now, I have lived long enough to know that in physics you never know what is the last word. But I do believe that today what Bohr said is still the best we know. So that is how it stands today. And I also think it will stand like that tomorrow.
Here's a look at what's coming up in business on BBC Learning.
Bye.